amazing. She really did good research. I'm impressed. Okay, yeah, so I'm super happy to be here. And I'm going to be talking about one of my favorite topics. So what I'm going to try to do in this talk is start at the very beginning, and I mean the very beginning, and then get to the current day. So I think that this is a topic that will be accessible, so I want to keep everyone with me, and one way to keep everyone with me at 5 p.m. after a long day of math talks is to make this very engaged. So please ask me questions. You don't need to raise your hand. Just shout them out at any time. I'm super receptive to questions at all times. Okay, so everything I mentioned that's going to be my own original work is joint, or almost everything is going to be joint with Eric Larson, who you can see here demonstrating how to interpolate a curve. Okay, so what is the problem I want to study? The problem is, when does there exist a curve of some given type, which we'll make more precise later, that passes through some collection of some number of points, which I'll call n. So here are my blue points, and I want a curve of some given type that interpolates through those points. And notice here, as you see in this picture, I want exact interpolation. This is not something about like curve of best fit or some statistical thing. I actually want the curve to pass through all of my specified points. Okay, is the basic problem clear? Great. So let's start at the beginning. So given 2 points, what types of curves can I interpolate through these points? A line, yes, okay, great. So what you all just told me is Euclid's first postulate, which is from 300 BC. So as I said, really the very beginning. There's a line through any 2 points. Okay, let's make this a little harder. What about 3 points? Circle. Yep, I can do a circle. Again, 300 BC. It's in Euclid's Elements. There's a circle through any 3 non-collinear points. So I want to point out this non-collinearity, right? If my points all were on a line, then I wouldn't be able to pass a circle through them. So that illustrates something that I'm going to bring up over and over again in this talk, which is I want my points to be sufficiently general. I want them to be in general position. If there was something special about them, I might not be able to interpolate that type of curve through them. Okay. So these 2 results from classical antiquity that I just mentioned can be found in Euclid's Elements. A line through any 2 points, a circle through any 3 general points. And this picture here is the oldest surviving fragment of a copy of Euclid's Elements from 200 AD, just to emphasize how really old this is. Okay, there's another result from classical antiquity, which comes from sort of taking this circle and making things a little bit more flexible. So a circle is one particular type of conic section, but it's a rather special type of conic section. You could ask for a more general conic section. How can you maybe interpolate that through more general points? And, well, oh no. Okay, and the answer is yes. So this is also classical. It can be, it's found in the collections of Pappus of Alexandria. So this is more recent, but still classical, 340 AD. Conic section can be interpolated through 5 general points. So here you see a little picture. And this title page that you see is from the first Latin translation of Pappus's collections. In the Renaissance, and this was actually incredibly influential on Renaissance mathematics when this was translated. Okay, so these might seem like really old and maybe elementary facts, but I just want you to think for a second how hard it is to prove Pappus's theorem if all you have is sort of elementary plane geometry. So you have these 5 points, and you need to give me a synthetic construction of this conic section through these points. So, you know, sit down with your compass and straight edge and construct the foci of this ellipse or something like that. So here's a more modern synthetic construction. I got this gift from Wikipedia, so it's going to repeat again. But you see there's 5 blue points, and this is some construction involving lines that traces out a hyperbola that goes through these points as time goes on. So it's really rather special, and you know, I think would be quite hard to discover on your own, these sort of synthetic constructions. Okay, so let's move forward quite a lot. So now we're going to move to the 1700s, and a big advance comes in the 1700s, which is the birth of algebraic geometry, my field. And the central insight of algebraic geometry is that curves have equations, right? It was so hard to find that conic section because we had to construct it with compass and straight edge. We couldn't write down the equation of the conic. So once we have equations, things get easier. So let's use this insight that curves have equations and go back to Pappus's theorem and prove it all here in this room right now. Okay, so we have to study conics. So what is a conic or a conic section? I'm going to shorten it to a conic. So it's a plane curve, a curve that lives in the xy plane, and it's specified by an equation of degree 2. So what that means is, here you see I have this equation. It's composed of monomials. Each monomial has total degree at most 2. And in order for the entire thing to have degree 2, I want to have some monomial that actually does have degree 2. But I have some flexibility of assigning these coefficients A, B, C, D, E, F, and assigning different coefficients gives me different conic sections. So what does this equation do for me? Well, it's a rule. It tells me when some point in the plane is on my conic curve, right? So you can use it to test if some point PQ is on my conic. Well, I just plug in P for X and Q for Y and see if I get 0. Everyone with me? Okay, great. So we're trying to interpolate conic sections through 5 points in the plane. Well, I have a rule for telling me when 1 point is on my conic. So let me just apply that rule 5 times. So if I have 5 points, P1, Q1 through P5, Q5, those are all simultaneously on a conic. If these 5 equations are all satisfied, okay, so we remember from the talk yesterday that we're not so good at solving equations, right? So maybe this is looking kind of bad. But then you remember that what we have is that we're given these 5 points. They're just numbers. So everything, the blue, hopefully that shows up. Everything in blue there is just a number. And what we want to do is we want to find an interpolating conic. So we want to find some A, B, C, D, E, F that makes all these equations 0. So we're trying to actually solve for those pink variables A, B, C, D, E, F. And now these 5 equations here, in terms of the pink variables, they're linear, right? Everything in blue is a number. So in terms of what we have to solve for, these are 5 linear equations. And those are the things we can do, right? Like we can't solve a lot of equations, but we can solve linear equations. So let's put this the way that we would put it as linear algebra students. Okay, so this A, B, C, D, E, F we want that will determine our conic for us is just a non-zero vector in the kernel of this matrix. And so what's the insight that gives you Pappus's theorem? It's that a matrix that has more columns than rows always has a non-zero kernel, right? So more columns than rows. Well, the columns, these are indexed by the possible monomials, these possible coefficients. So I need to have more coefficients here than points that I'm trying to interpolate. And so, well, I have 6 coefficients, so I can interpolate through at most 5 general points to always be guaranteed to have a non-zero kernel. All right. So where should we go from here? We just reproved this very classical theorem, but in one slide of rather elementary linear algebra. So let's generalize that a bit. Let's look at how many general points can you pass a degree D plane curve through? So a conic, that equation in X and Y, the total degree of every monomial was at most 2. So now I'm going to allow that total degree to be at most D for some input D. So how should I approach this problem? Don't be shy. Feel free to shout it out.
Can I write all monomials with degree at most D?
Great. I just want to count the coefficients, exactly as you said. So I want to figure out how many possible monomials I have with degree at most D, and then I'll be able to put a coefficient in front of each one of those. Great. So this is a kind of classic elementary combinatorics problem. So here's a nice way to see the answer to this problem. I'm going to arrange my coefficients. I'm going to arrange my possible monomials on different levels depending on, oh, sorry, this d minus 2 should be a d minus 1, depending on what the total degree was, right? Because I said total degree at most d. So everything on the top line is total degree equal to d. And then I put all the things equal to d minus 1, et cetera, down to degree 0. And now it's kind of easy to see how many there are, right? On the first line, there are d plus 1, then there are d, all the way down to 1. So the total number of coefficients is the sum of I from 1 to d plus 1, which is d plus 2 times d plus 1 over 2, or d plus 2 choose 2. So that's going to be the number of columns in my matrix, if I were to write out this matrix that I want to have a non-zero kernel. And, well, the number of general points I can interpolate through is 1 less than that, because I need to have strictly smaller number of rows than columns. And so I subtract 1, and I get d times d plus 3 over 2. All right. Any questions? Let me pause. Yeah.
What part of this argument uses the fact that the points are in general position?
Great. So nothing in this argument used the fact that the points were in general position. So what I showed is that for any collection of this many points, there is always a curve of degree at most d that passes through those points. Now, if the points were special, it might be that my curve is a kind of broken curve. Like let's think about the 5 points case, hypothesis theorem. If I made all those points be on a line, there would still be a conic passing through them, but it would contain that line. Maybe you wouldn't want to call that a conic. That's one thing. The other thing is that I'm claiming that this is an upper bound. I'm claiming that you can't add another point and still have a non-zero kernel. So I'm saying that this matrix, and in order for that to be true, I want them to be general points. Excellent question. Absolutely excellent. Keep the questions coming. Other questions? Okay, so sometimes this doesn't work. So what we just proved all together here is a classic theorem of Gabriel Kramer, who you see right here, very accomplished Swiss mathematician in the 1700s. So he proved that a plane curve of degree d can interpolate through d times d plus 3 over 2 general points and no more. And in fact, if your points are truly in general position, then these points determine the curve of degree d. So there is a unique curve that passes through those points, and that's related to the point I was saying before. So you need to have a non-zero kernel, but if that kernel is one-dimensional, then there will be a unique curve, because the curve is just specified by the vanishing of my equation. So if I scale all of the coefficients simultaneously, so if I have a one-dimensional subspace and I move in that subspace by a non-zero scalar, I get the same curve. All right. Everyone happy? Any questions? Yeah.
Does general position mean that those points don't lie on a cove? I guess definitionally, does it mean that they don't lie on a cove of no degree?
I mean, that could be one way in which they could be special, is if they lay on a curve of lower degree. Actually, this concept of general, I'm really allowed anything I want. I'm allowed to throw out any sort of relationships that you could possibly have between the points that constrain them to lie in some lower dimensional possibility. I'm allowed to throw out anything like that. So I'll say a bit more about where this general comes up, and if I don't answer your question later, then ping me back to it. Okay, other questions? Yeah.
If the null space has like dimension 2, for example, is there a meaningful way of like interpolating between the coefficients, like a convex combination?
Yes, if the null space had higher dimensions than 1, you would have an infinite family. You would be able to scale, start, here's one, here's another one, and you'd have all the possible scaling things that also pass through those points. Great question. Yes. Yeah.
Do they create a span of any sort?
Yes. So this is the curves that interpolate through, or the equations of the curves that interpolate through these points do form together with 0, do form a linear subspace because they are this kernel. And so, yeah, so does have that structure of a vector space. Yeah, great questions. Any other questions? Okay. So, Kramer, I just wanted to say one more thing about Kramer. Who's heard of Kramer's rule? Okay, this is Kramer. So Kramer's rule tells you how to write down solutions of systems of linear equations. So, I wonder why he was interested in that. This is the sort of problem he was working on. Okay. So I think it's now time for me to probably introduce the one interpolation problem you have the most chance of having heard of before, which is Waring-Lagrange interpolation. And I'll say a little bit about why I call it Waring/Lagrange interpolation. So this is for graphs of polynomials. So in this case, I'm going to, again, fix endpoints, P1, Q1 through Pn, Qn. And I'm going to ask if there's a degree D polynomial in one variable. So here's the general form of that polynomial, so that it sends each of my pi's to the specified output Qi. So I want a polynomial of degree D that takes specified outputs on n specified inputs. All right. So why does this fit in with the general theme that I've been talking about so far of interpolating curves through points? Well, I can plot these points in the xy plane, right? So here I'm plotting all the, P, that's my input that I want, and then I plot the point corresponding to the output that I want. And then when I'm asking for this f that takes a particular value, I'm asking for a graph of this function that interpolates through those points. So again, it fits the same theme of what I've been doing so far. Okay, so let's apply what we just learned about interpolating curves through points to solve this interpolation problem. So you know the drill. We should look at the coefficients, right? AD through A0 for a degree D polynomial, and we should write down the linear conditions on the linear equations on those coefficients in order for this polynomial to send pi to qi. So I'm not going to go into the details again. I think I've made you eat enough of your linear algebra vegetables for one talk. So, but if you wrote all this out, you would get this system of linear equations. It's no longer a homogeneous system, right? I'm not saying that some matrix times some indeterminate is 0. I'm actually specifying possibly a non-zero vector here. And so in order for this equation to have a solution, I want to have at least as many columns as rows. I don't need to have strictly greater because I don't have this scaling flexibility that I used to have. Okay. So the answer to the Waring-Lagrange interpolation problem of when I can interpolate this polynomial is if the number of coefficients, that's the number of columns, d plus 1, is at least the number of points, that's the number of rows, which is n. So I can fit a degree D polynomial through d plus 1 values. Okay, so that's the Waring-Lagrange interpolation theorem, which appears in this 1779 paper of Waring. So here's a picture of Waring, and you can see sporting the coolest hairdo in the room. So there exists a degree D polynomial f of x taking specified values on d plus 1 distinct inputs, p1 through pd plus 1. And in fact, if all these inputs are distinct, then it's unique. There is a unique such polynomial. So what I'm saying is those system of linear equations I wrote down before, if that matrix is in fact full rank, has a unique solution. And he published this in 1779 in this paper, which is very boldly titled Problems Concerning Interpolations. Lagrange rediscovered this formula and wrote a paper about it in 1795, quite a bit after Waring. But as, again, we saw yesterday, maybe things aren't fair. The person whose name is attached to this, I think, to the present day is Lagrange and not Waring. All right, so that was a bunch of linear algebra. Let me pause again and see if there are any questions about exploring Lagrange interpolation. Okay, so what I want to do next is like a little reset. So if you've seen enough linear algebra, just take a quick deep breath and reset. And I want to go into an application of this very beautiful classical result. So I hope I'm not going to date myself here. Does everyone remember what this is? Okay, great. Well, even if you don't remember that, you probably remember what this is, right? Okay, so, CDs and QR codes, they're both means of storing information digitally. And then you need to access this digitally stored information in some way. You need to, read the information after you've stored it. And so, is everyone? Okay, so you need to read the information after you've stored it. So, and often in reading digital information, it's possible that errors get introduced. And so what I want to talk about is how you can read digitally stored information while minimizing or being able to catch errors. Okay, so here's a toy version of this problem. Suppose you want to send n numbers, P1 through Pn. And you can imagine you're sending these numbers from a CD to a boombox or from your QR code to your cell phone or whatever. So this is my choices. Then you want to send n numbers, and you want to send these numbers in such a way that you've built in redundancy so that you can detect and correct errors in this information transfer. So does anyone have any ideas of how I could build in some redundancy in order to detect or correct errors? Yeah.
If you have them as like endpoints which determine a polynomial, you just pick more.
Don't score my punchline, but yes. Let's be more naive. How can I do this? Yes.
Send them each a bunch of times.
Yeah, send them each a bunch of times. That was the naive thing I wrote down. There are other naive ideas, but let's do the naive ideas first. Again, as came up in the talk yesterday, I want to illustrate how great interpolation is, so I want to compare it to something which is less great. So, okay, if you want to detect errors, just send each number twice, right? And then if I have a pair of numbers that are not the same, I know there was some error, and I go back and I read it again. Okay, that doesn't help me to correct errors, because if I have two different numbers, I don't know which one was right. I don't know which one I should take. So if I want to correct errors, maybe I could send each of them 3 times. And then if one of them gets messed up, I still just take whichever is most common and assume that that one's correct. So both of these naive things would work, but in the first one, I'm sending twice as many numbers, and in the second one, I'm sending 3 times as many numbers. And that's a lot more. I only wanted to send n numbers, and I have to send 2n or 3n. So much less good. Okay, so what I want to describe is a much better idea based on polynomials, which is due to Reed and Solomon, who you can see here. Here's their paper, Polynomial Codes Over Certain Finite Fields. And this idea has become known as Reed-Solomon error-correcting codes. So as was pointed out earlier, if I have these n numbers, P1 through Pn, this is what I want to send. I can use those numbers to construct a degree n-1 polynomial just by putting those as the coefficients of my polynomial. Right? Everyone with me? I just make a polynomial. Okay, so then instead of sending P1 through Pn, I could send the values of this polynomial on the first n numbers, f of 1 through f of n. Right? That's still n numbers. And because this is 1 more than the degree of my polynomial, it uniquely determines my polynomial. And so if I know f of 1 through f of n, that's the same as knowing P1 through Pn. Okay, so nothing special has happened. There's no magic yet, right? I wanted to send n numbers, I just send n different numbers, but they still determine it. So the magic is if you want to detect errors, just throw in 1 more number. Just over-determine your linear system. So that 1 more number will still lie on the graph of a degree n-1 polynomial. So you can still extract the correct polynomial out of it. You can still get P1 through Pn. But the good thing is that if one of my numbers gets a little messed up, then I have too many points and they won't lie on a degree n-1 polynomial, and I'll know that something went wrong. I'll be able to detect that there was an error and I'll go reread it. So this detecting, it doesn't allow me to correct errors because there are multiple graphs of degree n-1 polynomials that pass through all but one of these points, and I don't know which one's correct. So if I want to correct errors, well, I'll just throw in one more. And then one of those possible graphs of degree n-1 polynomials will have one more point on it than all the other ones, and now I know that one is the correct one. So this involves sending n+1 if you want to detect, or n+2 if you want to correct, but that's way better than 2n or 3n. So, yeah.
More than one error. Like, what
Great question. So what if you have more than one error? If you want to be able to detect k errors, you send k extra numbers, and if you want to correct k errors, you send k+1 extra numbers. Yeah, great question. So it depends, of course, it's a trade-off, whether you want to, what's the frequency that errors are introduced here? Yeah. Other questions? Yes.
It seems, this might be what we're going to get to, but it seems like for this to work, you need to have all of your information that you're transmitting, all of those bits of data lie on this polynomial, but that means you now can't transmit arbitrary information.
Well, okay, so what I want to transmit is P1 through Pn. Do you agree? I only want to transmit n things.
Oh.
And I get to send as many outputs of this polynomial that I've built out of P1 through Pn. And those will, by definition, always lie on this because they are the outputs.
Right, okay, right. That makes sense.
Great. Other questions? Yeah.
There is still a possibility that there's error in our corrected term, so f n+1, yeah?
I mean, well, it could be error in one of these. It could be that now, so I think you're sort of hinting at what if there are more errors, and then you have to send more points if you think that there's a probability of being more errors. But yes, of course, all of this is, you have to fine tune it to send the right amount of data so that you're not sending way too much data given the frequency of errors. Great question. I think there was a question here. Yeah.
In the naive solution, it's very easy to see if there's an error and just look at the error. And here you kind of have to do calculations and do a bunch of cases, etc. How is it fast or not so much?
Well, okay, so I'm a pure mathematician, but let me say, this is what is used in CDs and QR codes and basically any digital storage media use Reed-Solomon codes to this day. So I think that it has, the test of time, it has passed the test of time, because how efficient is this? It's very efficient. So it's passed the test of time. Yes.
So the F1, F n+1, F2, does that check for errors on one value or multiple values at a time?
Just this will allow you to, well, let me go back to the detecting. This will allow you to detect if there is at most one error. If there are more errors, then it's possible, you won't be able to detect it from.
So only one point at a time.
I mean, just some error. You won't be able to know where the error is because if you knew where the error was, you could maybe correct that error. But yeah. Yeah, great questions. Yeah.
I could imagine a really bad error creation system, accidentally adds one to all inputs, but that isn't recognized by this. You'd still be able to create a polynomial if you're shifting everything over by one.
Yeah, so this is assuming that your errors are sort of the random errors in, glitching reading a CD or something. It's not assuming that there are systematic errors. Somebody described to me when you're doing this sort of thing, you get to wear the black hat. You're not proving a theorem that always works. You're trying to get something that works most of the time so that it has practical relevance.
Is there a way to handle more systematic errors?
I don't know, that's a good question. Coding theory is a very active theory of mathematics, so yeah. Yeah, okay, lots of questions. I'll go in the back and then I'll come over here. Yeah.
So maybe it's time to ask this question. What is the benefit of using the Warren-Lagrange point interpolation method compared to something like the Bezier point interpolation method?
Okay, what's the practical importance for Reed-Solomon codes? I mean,
Well, what's the benefit of using this specific form of point interpolation? Like, why not use, why use this specific method to generate your function?
well, so I'm not an expert on Bezier curves, but I think what you do is you interpolate curves and also you require like tangential information at the points that you're interpolating. Is that correct?
Yeah.
So that's a more general form of this. You can write down the linear equation. Now you'll have equations, that involve derivatives too, and you could also work, you could work out all of those problems too. That's a very great point. And in the 1700s, 1700s and 1800s, when all of this was being developed, they were doing those problems too.
Okay.
Yes, great question. Other questions down here in the front? Yes.
Here using n inputs to determine the n coefficients, right?
Yeah.
Before we saw the like ellipse kind of thing and degree d things, we only needed n points to determine a thing that had d squared coefficients, right?
Well, so in general, okay, so this is slightly different, this graph of polynomial functions versus general degree something polynomials in two variables, so the numbers were slightly different, but in that case, but in all cases, you want sort of a non-zero solution to a system of linear equations, and it might be up to scaling or not, so you might have it off by one or not off by one. But you're thinking the way I want you guys to think, which is, sort of what's special about this maximum n. So keep that in the back of your head because we're going to come to that in a more general case. So let me take one more question, then I think I should move on. Okay, I scared everyone. So I just have one technical thing I want to say, which is that in practice, we don't want all these, we don't want numbers to get too big when we plug them into this large degree polynomial. So we work over some finite field, which is why that Reed-Solomon paper was called polynomial codes over certain finite fields. Then none of our coefficients will get too big. So that was just a technical point so that I'm not lying here. Yes.
I know that over finite fields, polynomials aren't always determined by like their values and inputs.
Right, but this interpolation still holds
Okay.
because it's just linear algebra.
Okay.
Yes, these will be determined by their values of these things. Yeah. Okay. Other questions? Okay. So so where do we go from here? Maybe the fact that this is messing up is giving away. So there's many possible things we could do. So here's one possible thing that we could do is we could try to move into higher dimensional spaces and still consider single equations in higher dimensional spaces. So that means some polynomial that involves more than just two variables. So it could involve three variables, x, y, and z. And so, well, the thing which is the solutions of those types of polynomial equations, those are higher dimensional algebraic varieties, hypersurfaces, and you could try to interpolate those higher dimensional algebraic varieties through points. So here's an example, something that's specified by a polynomial equation of degree 2 in 3 variables is called a quadric surface. Here's a generic picture of what it looks like over the real numbers. And you know the drill. Well, I look at the number of coefficients. There are 10 coefficients here, so I should be able to interpolate quadric surfaces through 9 general points. Okay, was that fun? Not really, right? Because we already sort of knew how to deal with this, right? This was just linear algebra. So, well, remember this quadric and these 9 general points, because this is going to come up again. But we want to do something new. So let's continue to work with curves. Let's stick with curves, one-dimensional things, but we'll allow more types of curves. We won't just look at curves in the plane specified by a degree D equation. We'll generalize this. So here's my curve. So one way we can generalize this type is we can stick it in a higher dimensional space. So This is an R-dimensional space. A joke my advisor used to tell is you can tell R-dimensional space away from two-dimensional space because it's bigger. So I tried to draw a big circle. Okay, so it's an R-dimensional space for some value of R. And now we need some notion of degree, which was like the degree of the defining equation of a curve in the plane. So let's go back and think about that for a second. So if I have a degree D equation that defines my curve in the plane, if I restrict that degree D equation to any line, I get a degree D equation in just one variable on that line. And by the fundamental theorem of algebra, that has D roots over the complex numbers, with appropriate multiplicity. So I can make that sort of thing work in general in a larger dimensional space. Instead of restricting to a line, I restrict to a hyperplane, some linear subspace of dimension 1 less than the total space. This will meet my curve in D points counted with multiplicity, and that D is the degree. So there's still a notion of degree. It's not something about the degree of the polynomial equation, but there is a well-defined notion. So, okay, so I'm generalizing my type, R-dimensional space, degree D. There's one more invariant of these curves, which is the genus. So the genus is a topological invariant of an algebraic curve, which may or may not be familiar to you from topology. So if I look at the complex points of my curve, so you can think about this as sort of complex solutions to these equations, it's a compact Riemann surface. So it could be genus 0, it could look like a sphere, or it could be genus 1, it could look like a one-hole donut, or in general, genus G will have G holes. So there's this other invariant. So, okay, so let's return. So that's this invariant that I want here. So I'm going to look at curves in R-dimensional space of degree D and genus G. Okay, so here was my main question from the beginning, from the very first slide. When does there exist a curve of given type through a collection of endpoints? So I can ask a more refined question. When does there exist a curve of degree D and genus G in an R-dimensional space through a collection of n general points? So this is going to depend on all of these natural numbers: the degree, the genus, the dimension of my space, and the number of points. And I'm really asking here, what's the maximum number of points I'm allowed to put here so that I can still find an interpolating curve? Okay, so if you're given this very natural question, the thing that you need to do to attack this question is you need to think, what am I even trying to prove? So like, what should n be? Can I formulate a conjecture that will give me something to try to prove? So I think that we can all here work through to try to formulate a conjecture for this n. So that's what I want to do next. Okay, so in order to do that, let's revisit some things where we did actually know what n was. So let's go back to Kramer's theorem, which says a degree D plane curve, not degree D plane, a degree D plane curve can interpolate through at most d times d plus 3 over 2 general points. So in that case, we knew what n was. Okay, so how did we get that number? Can someone remind me? Yeah, we counted the coefficients, right? We looked at the equation, and we counted the coefficient. Okay, so I have some bad news. A curve in an R-dimensional space is usually not specified by R-1 equations. So it's not like each equation cuts down the dimension by 1, and once I get to 1, I have a curve. I mean, well, usually that is true, but not all curves arise in that way. So that means if I just looked at the equations of these curves, there's some weird non-linear conditions that the coefficients need to satisfy in order to give me a curve. And now I'm going to have to solve some solutions that involve these really non-linear things in the coefficients. And as we know from the talk yesterday, I can't do that. Not possible. So we need some other way of attacking this than looking at the equations. So I want to go back to this d times d plus 3 over 2 and interpret that in another way for you, which will allow me to generalize it to curves in higher dimensional spaces. Okay, so where does this number come from? Well, so now this is a schematic of, little squishy picture to give you the idea of what's going on. None of my drawings on this slide honestly mean things. So don't think about what the blobs are, they're schematics. So what is this d times d plus 3 over 2? I could form a parameter space for degree d plane curves. So what does that mean? It means I have some sort of space, and the points of this space correspond to the possible degree d plane curves. So as I move along my points, I get different degree d plane curves if I move around in this parameter space. And what is this parameter space? It's basically just the possible coefficients, right? It's like AD0, blah, 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 all those coefficients I wrote down. And there's one piece of freedom, which is that I just scale all the coefficients, I still get the same curve, right? Because the curve only depends on where they vanish. So the dimension of this space should be d times d plus 3 over 2, which was the total number of coefficients minus 1. Is everyone with me? Make sense to everyone? Okay. So now I have this d times d plus 3 over 2 possible plane curves of degree d, and I want them to pass through a point. And if I think, okay, if I have this curve, in order to pass through a point, it's sort of, I need a one-dimensional family of these curves in order to hit that point, right? I'm thinking about this point in the plane, and I'm moving in my plane, I need a one-dimensional family to hit it. So I'm going to make that argument I just did with my point, my hand and my arm, more precise in what follows, but if that makes sense to you, then just keep that in your head. Okay, so I have this space of degree d plane curves, which has this dimension from the equation. Okay, so I can make a new space, which is very related to this space of degree d plane curves, but the points of this space are going to correspond to degree d plane curves that are marked with n points on them in some position. So it's a choice of a plane curve, and then some choice of n points on that plane curve. And of course, there's a map from this upper purple space to the pink space, which is just forget the points, right? If I have a curve, I can forget the markings of the points and just remember the curve. And the fibers of this map are all the possible ways I can put n points on a curve, right? So what's the dimension of the fibers? Well, each of those points can move in a one-dimensional family because they're moving on the curve, which is one-dimensional, and I have n of them, so the fibers are of dimension n. So this purple space at the top is of dimension d times d plus 3 over 2 plus n. Okay, so now I have another space, so the purple space is the same, nothing changed, but there's another thing I can do from an n-marked degree d curve, which is I can forget the curve and just remember the points in the plane. So I can map to this blue space, which is the possible configuration of n points in a two-dimensional space. Everyone still with me? Okay, so I have a map from here to here, forget the curve. And this bottom space has dimension 2n, basically for the same reason, the same way I calculated the fiber dimension before. So now I have a two-dimensional landscape that each of my points can move in. So each one gets to move in 2 dimensions. I have n of them. I have 2 n dimensions. Okay, so now we get to what does general mean? So what is the interpolation problem? It's saying if I fix a general point in this base space, in other words, if I fix a general collection of n points, when can I thread a curve through them? In other words, when is that point in the image of this map? Does everyone agree? So I don't quite need this map to be surjective. I just want it to be close to surjective. And what we call that is dominant. Basically, a general point here has to be in the image of this map. Okay, so, but just think about it like surjective. So I want this to be like a surjective map in this algebraic world of algebraic geometry. So if you remember from vector spaces or something, when can I have a surjective map of vector spaces? Well, the dimension of the source needs to be at least the dimension of the target. If the source is smaller, there's no way it's going to cover the target, right? Okay, so a necessary condition is that the dimension of the source, d times d plus 3 over 2 plus n, is at least 2n. Everyone agree? And do you see that we get Kramer's result out of this? Right? We get, subtracting this n to the other side, we get that n is at most d times d plus 3 over 2, which is what we wanted. Okay, this seems great, right? So now we can just move on, right? We have some let's work in an r-dimensional space. Let's think of all the configurations of n points in an r-dimensional space. That now has dimension r times n, right? Because each one now has an r-dimensional space to move in. And I want to know when is a general point here in the image of a map from some parameter space that gives me genus G curves in r-dimensional space of degree n, the degree d with n marked points on them, right? Okay, so if I want to know when a general point here is in the image, and I want to formulate a conjecture about this, I just want to know what is the dimension of this parameter space of these genus G curves in r-dimensional space of degree d with n marked points on it, which should be n more than the dimension of just the unmarked curves. Everyone with me on this? Okay. So, who knows what this means?
Danger.
Danger, yes. How would you very literally read it out? What does it mean? Curves ahead. I love it because it means danger and it also means there's more curves coming. Okay. So okay, that strategy, right? I had this great strategy outlined for you. So now I have some bad news. So the first bad news is that this moduli space can have multiple components. So that one blob that I drew up there, that's a total blob. There can be lots of different blobs, okay? And these components can have different dimensions. So what did I even mean when I said we were going to compute this dimension and form a conjecture from that dimension? And moreover, these different components can have arbitrarily bad local structure. They can just be really, really nasty. And the curves in them can be really hard to describe. So maybe it looks like that very optimistic plan I outlined on the previous slide is just doomed to failure. And well, I wouldn't be here if it was totally doomed to failure. So there's a solution, and the solution is Brill-Noether theory. So this is, I think, a really beautiful subject that illustrates the combined effort of many different mathematicians in the 1980s. So Griffiths, Harris, Gieseker, Fulton, Lazarsfeld, and Eisenbud, to name a few that go into what I want to write here. So let me first say what we're going to do. We're going to pick out just one of those multiple components. So there were tons of components. We're going to be able to pick out one of them. And furthermore, that one component, we're going to be able to compute its dimension. And it's going to have really nice structure, and we'll be able to understand the curves in that component. So what does it say? So it says, when this numerical quantity, rho of GRD is greater than or equal to 0, so it doesn't really matter what this rho is, but here it is explicitly, then there's a unique component, which I'm calling MGRD circ. And what's special about this component is that the genus G curves in this component are general genus G curves. They're not like special or weird or have some particular moduli theoretic constraints. They're general genus G curves. And conversely, if this numerical quantity is less than 0, there is no such component. So any of those curves have to be sort of constrained and special in their moduli. So this is the natural class of curves to study, are these general curves, which are subject to this inequality, and they have one nice irreducible component in moduli. And we call these curves Brill-Noether curves because this is called the Brill-Noether theorem. All right, so I told you that it was going to single out a component, and it also gives us the dimension of this component. So here's the dimension. It's r plus 1 times d minus r minus 3 times g minus 1. Doesn't really matter. Just know that you can determine the dimension just from these invariants that I wrote down. So now I hope everyone is excited. Are you all excited? Because now we can formulate a conjecture. So here's the conjecture. A Brill-Noether curve of degree d and genus G in r-dimensional space interpolates through n general points if and only if, well, remember we had to compare the dimension of the top space with the bottom space. Dimension of the bottom space was r times n. That was easy to compute. The top space was this MGRDN circ, whose dimension is the dimension of MGRD, which is this quantity here from the Brill-Noether theorem, plus n. So rearranging this n over to the other side you see r plus 1d minus r minus 3g minus 1 over r minus 1 should be the maximum number of points. Everyone with me? Great. So let me illustrate one special case, which is when r equals 3. So when r equals 3, this r minus 3 drops out, and this formula simplifies to 4d over 2, in other words, 2d. So if I'm in three-dimensional space, that's like our physical three-dimensional space, I can expect to interpolate a degree d Will-Noether curve through twice the degree 2d general points. All right. So what do you do once you formulate a conjecture? Maybe you prove it. What else do you do? Maybe before you try to prove it, what should you try to do? Find a counterexample. Great. Always a good first step. So here's an example. Degree 6, genus 4 in our three-dimensional space. Okay, so remember, so R is 3. That's that special case that I simplified out for you. So the conjecture predicts that such curves can pass through twice the degree, so 12 general points. Okay, but here's a fact from algebraic geometry that once you've taken a first course in algebraic geometry that covers algebraic curves, you should be able to prove any such curve with these invariants always lies on a quadric surface. Remember, this was that thing I brought up before. So this is the vanishing of a single equation in 3 variables of degree 2. Okay, so who remembers what I said about quadric surfaces? They interpolate through 9 points. Okay, so can you have 12 general points that lie on a quadric surface? No, because they only pass through 9 general points. Okay, so we're sad, right? We just had this great conjecture. It involved the Will-Noether theorem, and now we have a counterexample right away. And in fact, maybe we're more sad even because there's another counterexample. If we take degree 5 curves in genus 2 in 3-dimensional space, they also lie on quadric surfaces, so they can interpolate through at most 9 general points, but twice the degree is 10. Okay, so this is looking pretty bad, right? But it's not so bad. So here's the first paper I wrote in grad school. You can see it's archived in 2016. And so exactly deals with this r equals 3 case. So a Will-Noether curve, a space curve, a curve with r equals 3 of degree d and genus g interpolates through twice the degree number of general points if and only if it's not one of exactly those 2 counterexamples I showed you. So I really like this theorem. You're all laughing. but I like it. I like it precisely because you guys are laughing, right? Like, how many results in math are either completely true or like pathologically everything goes wrong? But this is true with exactly 2 counterexamples. Okay, so that was the case r equals 3. So then now I teamed up with Eric Larson, and in 2017, the next year, we tackled the case of r equals 4. And in fact, when r equals 4, there are no counterexamples. So a Will-Noether curve of degree d and genus g in 4-dimensional space interpolates through exactly the number of general points predicted by that conjecture, which is this. Okay, so I think probably you all are appreciating that I have an excellent strategy for producing an infinite number of papers. Where, so by induction, what do you think I did in 2018? No. No, in 2018, I started working on the general case, and which is much harder than just doing these specific cases. And so I didn't finish it in 2018, I didn't finish it in 2019, and I didn't finish it in 2020 or in 2021, but in 2022, we solved the full conjecture. So this, again, joint work with Eric Larson just from this year. So a Will-Noether curve of degree d and genus g in r-dimensional space interpolates through the predicted number of general points, if and only if it's not one of these 4 counterexamples. so here are those 2 you just saw when r is 3, 5, 2, 3, and 6, 4, 3. And each of these has a similar counterexample in 5-dimensional space, so no counterexamples in 4. There's nothing here. And then this 5, 2, 3 is kind of similar to this 7, 2, 5, and 6, 4, 3 is similar to 10, 6, 5. And there are no counterexamples after 5-dimensional space. Yes?
So maybe this is not a good question because it's very non-mathematical, but you feel like there's a philosophical reason why there are these counterexamples, or does it feel just kind of random and you found that these are counterexamples and when we leave them out then it works?
These counterexamples all sort of happen because of the way that these curves are forced to have maps, low degree maps to a line. So these two, this 523 and 725, these are forced to have degree 2 maps to a line. And these 643 and 1065, these are, they're forced to have certain degree maps to a line. And from those, you can construct surfaces in these spaces that they lie on. And those surfaces don't pass to the right number of points. So you're like, why can't you keep going to higher spaces? Well, it depends on the invariance of those surfaces. And those invariants, once you get to dimensions greater than 5, they never make things go wrong. So these live in an infinite family of examples. It's just they're only counterexamples when it's small. So I would say it's sort of a coincidence of small numbers. Yeah. Yes.
So you were able to see good justification for those in your initial paper for only 2 counterexamples, and that the rest of the examples would be the criteria for having.
Yes. So there's this is an if and only if. So yes, great question. This theorem is an if and only if. So there's 2 directions. The direction that these are all counterexamples, there are good geometric reasons for those. The really hard part of this theorem is proving that nothing else is a counterexample, which is really hard. This is a 70-page paper, shrunk to as small as possible. And let me say the fact that there are counterexamples makes this theorem even harder, because the way that we prove this is we develop ways of reducing these this problem for d, g, and r to smaller d, smaller r, smaller g. So we do some huge induction on this 3-dimensional possible lattice of these d, g's, and r's. And so if you have this huge induction, your induction has to be complicated enough so that you never have an arrow that points down to a counterexample, right? You start with this, you can never get a base case that's a counterexample. So you have to have some really complicated arrows to get down to exactly miss the counterexamples at the bottom. So not only does this, I think, make it a cooler result, it makes it harder to prove. Okay, so before I end, let me just say, if there's any moral to this whole story, it's that, well, I went to an REU too when I was an undergrad, and it was great. In 6 weeks, I got introduced to a problem, I solved the problem, I wrote a paper, I gave a talk. It was amazing. Solving a problem in 6 weeks was great. But you know what's also great? Starting working on something in 2016 and finishing it in 2022. So I think the moral is mathematical persistence prevails, and it's really nice when it works out. So I'll stop there.
So thank you again for the wonderful talk, spanning a significant history of mathematics, even right up to the present year.
Yeah.
So any additional questions for Chris?
So now that you've proven this incredibly generalized result, is there anything left for us to do in it? What would be the next steps?
I mean, well, there is always higher dimensional cases. So even when this, you could look at surfaces that aren't specified by a single equation or even the right number of equations, it's a much harder problem. You could also look at, so I was sort of looking at curves in secretly, it's right here, projective space of dimension 4. I was just calling it 4-dimensional space to be ambiguous, but you could replace that with something else. So there's other things algebraic geometers like you could try to interpolate curves through points in a Grassmannian, which is a certain parameter space, and that has a very concrete interpretation in terms of projective bundles over those curves. So I mean, even if you want to stick with curves, you could replace this with a different space. Here's another question. In the Brill-Noether range, you still have these different components. So the Brill-Noether range, when this inequality is greater than or equal to 0, you still have other components. It's just that one of them is singled out. So you could try to ask, well, what's the maximum number of points I can interpolate through on those other components? Maybe it's always less than the maximum you could interpolate through on the Brill-Noether component. That would be amazing if interpolation specifies the Brill-Noether component for you. I'm not saying that's true, but you could ask those sort of questions. So yeah, there's still more to do. Oh, let me say one more thing, sorry, which is you could try to interpolate curves through special configurations of points, right? So I was doing general points, but what if you constrain some of your points to lie in a hyperplane or something like that? So the circle problem, possibly, some of you know, what is a circle? It's a conic section that passes through two special points at infinity. And so if you want to, say interpolate your curves through mostly general points, but some specified points contained in the hyperplane, that could be an interesting problem.
And then,
Yeah, I was wondering if you could just talk a little bit about the process of working on this one question for the past 5 or 6 years. I guess that you weren't having like consistent, encouraging progress that whole time. So what was that like?
Right. Well, I did work on other things too, so it's not like I just crawled into a hole. But yes, you're right. I think that we would probably in about 2018 or 2019, we had a good idea of how to construct one of these arrows to go down. And so that gave us confidence that we could attack this whole problem. So then, maybe in 2018 or 2019, we're like, oh, we can do the whole problem. We constructed this really great arrow going down. Okay, well, it took 3 more years to prove that we had enough arrows to get all the cases. So, but we had some confidence that we had a good idea, and that let us keep going. Yeah, good question.
So it seems like we started, or like I guess the middle third of the talk, we were interested in like conic sections or polynomials in R2. So those are pretty tame functions as far as functions go, and then you kind of went wild and crazy with R-dimensional curves. So I'm wondering, is there actual study into like, say, parametric curves in R2, something that's like medium tame?
Let me see if I understand your question. Are you asking like, maybe I don't care, wait, let me say maybe this is not what you're asking, but let me answer one question, and then if you want me to answer something else, I'll tell you. So here's a related question. I have a curve, some abstract curve, and I have some points on this abstract curve, and I want to map from this curve to the plane so that those points are mapped to specific points. That's kind of more like the Lagrange problem, but for curve mapping to the plane, and that's a related problem, and it turns out it's much easier. So that is known, how many points you can specify like that. But maybe you wanted something else.
No, I'm happy with that answer.
Okay.
Thank you.
I don't know who to call on. Do you?
Yes.
There's no way to do you think you could use a similar approach with not like just one curves through the higher function space, but like say for surfaces? Like, would it be a similar approach of somehow finding the space of dimensions of like in higher dimension space and fixing points and you would find like the same way, but like you would have to add say 2 limits.
Yeah, so you could use that sort of technique for other things to guess a conjecture. You then have to have some way of proving that conjecture, which might be harder for surfaces. But yes, you could set up these sort of naive dimension counts, and the natural conjecture is that when these naive dimension counts allow it, you can do it. Did that answer your question?
I think let's take 2 more. Oh, sorry. So then here and then back here. And then also I wanted to say that I believe all of our plenary speakers will be available for breakfast tomorrow, so you can feel free to chat with them as well.
I was going to call you. Yeah.
Does it make any sense to make an error correcting code out of this type of
That would be really cool. So let me say 2 things that you would need to worry about. So one thing which, I purposely sort of left some things off. I didn't say them so that people could ask me about them, maybe. So one thing is, remember in Kramer's theorem, there was a unique, or in Lagrange interpolation, there was a unique thing. In these cases, it's not expected to be unique, but people don't know the numbers that pass through it. So you wouldn't uniquely specify it, but maybe if you send more data, you could specify it. That's one thing. The other thing is, we would need this to work over finite fields so that the things you're sending don't get too big. And a great thing about this theorem is it actually works in positive characteristics, so that's nice. But it doesn't tell you about like field of definition. It doesn't tell you like this curve is defined over this finite field. It tells you it would be like defined over the algebraic closure of that finite field. So some more work is needed, but I mean, at some point when we were grad students, we were talking to someone in coding theory who like wanted to use more general interpolation problems for error correcting code. So it definitely makes sense. Yeah, great questions.
And was there a hand to backtrack off? All right, let's take back to vote again. We'll take a picture. I'll come to the math hour. If you want to grab